Thank you, Thomas, for such a generous introduction. And I want to say how much I have valued the work of the UG Green Institute in really opening the space for dialogue and conversation in Guyana at this moment when Guyana is very much at this fulcrum in moving forward as a country with tremendous possibilities of economic development, alongside, of course, the challenge of addressing issues of how do you do this as a small developing country that has such an amazing ecosystem, which is of such great value. In fact, it's a priceless value to the world as a whole. I want to, before I say I welcome Professor Schlosser to speak, I just want to make a few remarks related to how what an interesting place we are today. Today, I think many of you would know today marked the end of the World Economic Forum's Davos 2023 meeting. And at that meeting there, among all of the challenges that were raised, the theme of that meeting was cooperation in a fragmented world. There were three important takeaways which the organizers identified. One is scaling climate ambition. Secondly, equitable growth. And thirdly, unlocking the benefits of frontier technologies. And I think in many respects, Peter, you'll be addressing these either directly or tangentially in the presentation that you will be doing. I want to recognize, of course, that this year also marks the 60th anniversary of our very own University of Guyana, and what a pleasure it is to have the Vice President and Vice Provost of ASU as part of what may be the last of this series of dialogues. And the reason why I say that is because I'm very pleased with the strategic relationship that ASU and UG have founded. And within that, of course, I know that there are many there's a lot of work being done between the two institutions. I recognize in the audience my good friend from my youth, Patrick Ketwaru, who is doing his PhD at ASU as part of that Scottish program of scholars. So it's really, I think, wonderful that PTU can be here talking to us on this very important topic. Professor Schlosser holds joint appointments in the School of Sustainability, the School of Earth and Space Exploration, in the College of Liberal Arts and Sciences, and the School of Sustainable Engineering and the Built Environment in the IRA Fulton Schools of Engineering. And it's really a symbol of the kind of transdisciplinary work that ASU is really championing. That it brings together all of these different multiple disciplines together to the table. So without further ado, I would like to invite Peter, you to come forward and speak to us. Thank you.
Thank you very much, David, Thomas, Jay, everybody, for the invitation to speak to you. I will try to share the screen now. So I hope.
Yeah, we can see that. We can see that. Thank you.
Okay. So what I will try to do today is to give you a sense of where are we standing with climate change, but do that in the context of the general pressure that we are putting on our planet from different directions. So most of what I will talk about is climate related, but I frame it in the context of where's the world really standing. And when I talk about climate change, I will look at what is the state of the climate system, what is the impact of climate change, and then allude to what kind of solutions we think we will have. So if we are looking at our planet right now, we see a planet that's under pressure. And of course, the question is, how did we get here? We clearly have entered the Anthropocene. This is a new geological era that is characterized by human activity. We can feel fingerprint of human activity from the deep sea to outer space. Everywhere you look, you will find some expression of human activities. And in a way, since quite a while, definitely since the beginning of the Industrial Revolution, we are shaping and engineering our planet on global scales, from local to global scales, typically in a stochastical way. We did not really think through carefully a lot of these planetary engineering actions. That led to the fact that in the language of the planetary boundary hypothesis, that humankind has left its safe operating space. Now, why are we saying that? What are we seeing? We are seeing more extremes at more places, different kinds, and at higher amplitudes. And further down in the talk, I will show you a few examples just to remind you, not that it would need to remind you, but just to get us all in the same space. Now, humankind has faced a lot of challenges in the past, always was able to deal with them. What distinguishes the present situation from what we went through in the past is that the time scale on which we have to act is extremely short. And climate, as I will lay out in the talk, is one example of a situation that puts pressure on us and where the time to react to it is very, very short, and where in a way you could say we have actually slept through at least half a century of warnings, and we are now in what you could call negative time. We are behind the timeline that we had laid out for ourselves in the past. So one of the main reasons that we often don't really want to talk about that brought us into the situation that we are now is population dynamics. We have more than 8 billion people on the planet. We are moving towards 10, maybe 10 plus billion by the middle of the century. And if you look at the underlying problem of climate change, it is that a lot of people are using a lot of energy from the wrong source, meaning that if we are using fossils, we are releasing CO2, which is the major greenhouse gas in the atmosphere right now. About 2/3 of the greenhouse gases is carbon dioxide. And that leads to warming on a global scale with local impressions. And I will show how that actually expresses itself. So that raises the question of what is actually the carrying capacity of the planet that would allow humankind to live in balance with nature, to use what the life-supporting systems can offer without overusing them, so that we bring them close to collapse. And biodiversity was mentioned before. It's one of the issues, but it's also depleting other resources. And in the process of doing that, creating side effects such as climate change. Climate change is not the root cause of the problems that we find ourselves in. It's an outcome of many of the actions that we have taken, but it is one that we feel pretty directly, because everybody can feel temperature, everybody understands what it means if precipitation patterns are changing, rainfall patterns are changing, because you can have floods, you can have droughts, and we experience them. So that's, I think, why climate moved into the center of discussion in many instances, although it is not the fundamental issue that we have to address. So if we are looking at how does energy and climate, because I made that connection, hang together, if you're looking at the, I'm not sure if we can, if you actually can see, here's the, I hope you can see the mouse here, the pointer. If you're looking from 1800 to pretty much now, and you look at the energy consumption, we are using, it's a de facto exponential function. We are using a lot of energy, increasingly so, and the bulk of it is coming from coal, oil, and increasingly gas now. So now there are renewables coming in, but at this point, fairly small amount. Now, if we're looking at the right-hand picture here, you can see that with the energy consumption that is coming from fossil fuels, here we go from the year 1000 to pretty much to the present, the carbon emissions started to increase, and then at the beginning of the Industrial Revolution, they really took off in an exponential fashion. Along with it, as you would expect, CO2 concentration of the atmosphere go up, and then here is the temperature. And as we would expect from fundamental physical and physical chemical laws, the temperature goes up too. So they go hand in hand, and we know that actually from past records of climate that we can read from tree rings and from ice cores. So that then leads to the following picture. If we are starting with the right side here, that's the temperature from roughly the time when the Industrial Revolution started to 2022. That's this last point. And you see it's up and down because we are living on a complex system that has its variations. There is quite a bit of variability, but there's also a trend, that's a secular trend that's overlying this variability that we could call just an intrinsic feature of any kind of complex system, and the climate system is such a system. If we are looking at what happened between, let's say, 1880 and 2022, it's this blue bar, it's about 1.2 degrees Celsius. That is pretty close to the 1.5, and I will get back to explaining what 1.2 actually means and what 1.5 means. We also see here on the left side how that looks if we are looking at the globe and we are looking at temperature anomalies compared to this time period. All the warm colors indicate that there is heating and warming, and there are a few areas, as you would expect in a global system that has complexity in it. There are a few areas where you have a little bit of cooling. You also see that the warming is distributed unevenly. There is a marked increase of warming towards high northern latitudes, often called the Arctic amplification. So if we are looking then at, that was 2020, was the warming was, because it was the last really hot year, 21 and 22 were a little bit lower. That tied, 2020 tied the record with 2016, where the warming was about 1.02 compared to a reference point, which is different than that reference point. And that really is, where we are right now. We're still increasing the temperature. If you look at the last 8 hottest years, they were in the past decade. So there is a clear trend here. So if we are looking now at the planet and we are looking at what are we seeing that is a consequence of the pressure we are imposing on it, then these are just a few examples between 2019 and today. 2020 was the warmest year on record. I just talked about that. We have wildfires to an extent that they create microclimates. We have the so-called death, the disappearance of glaciers in iconic places such as Iceland and Switzerland. Here where we live, we have heat records in Phoenix, across Arizona, but it's not just climate. Again, we have to see it in a bigger picture. We have plastic everywhere. You probably saw pictures of plastic in the ocean. Everybody on the screen here has the equivalent of 1 credit card worth of microplastics in your bodies. So this truly is everywhere, and fortunately most of it is inert, but about 1/3 actually can lead to reactions that will have health effects. But beyond the environment, we also have social and economic disruptions. Some of them by extreme weather and related phenomena, but others are simply societal instabilities protest movements, we saw cities on fire, nationally, globally. We see the reaction to that from our youth movements, Fridays for Future, Extinction Rebellion, Last Generation. You heard all of them. And if that's not enough, we also have experienced during the past several years a shock to the system that touched on everything that was from a virus, COVID-19, the coronavirus. And we thought we would actually have our hands full with that. About 6.5 to 8 million people lost their lives to that virus. Along came the Ukraine war, the Russia-Ukraine conflict. And that actually puts another perturbation into the system, throws us back into warfare similar to what we saw during World War II, which we thought we never would see again. But it also had impact on the energy landscape, on the progress we made and the pace we made moving forward with the agenda of getting off fossils and into more renewables. Just to bring back some of the pictures to set the stage for what I will show later, we had this inferno in Australia where we actually lost the lives of about 2 billion animals. About 2/3 of the koala bear population perished. Australia is hot, so you would say, yeah, right, not that unexpected. But we have increasing occurrences of large wildfires in Siberia. So here in 21, we lost 10 million acres of boreal forest in a record drought. We have hurricanes. We always had hurricanes. The hurricane frequency actually is not changing that much. What changes is the size of the hurricanes and the capacity to hold water that they have. Because if they go over warmer water, because of the increased water vapor pressure, which follows an exponential function, they can hold more water. They are mighty. So in August 2021, almost at the same time of the year when Hurricane Katrina hit New Orleans, Ida was moving towards roughly the same area. It had a diameter that is the entire north-south extent of Germany, and it unloaded tons of water. The interesting feature here is that a lot of these hurricanes now stall and dump their moisture content in form of precipitation into areas and flood them in a way that we never have seen. They also have the power and the amount of water that they can actually go across the entire continent. Most of the death toll from Ida was not in the area of New Orleans, it was in New Jersey, because at that point it hit cold air masses and it rained out and flooded large areas. So we are seeing new phenomena that in principle we understand, but we have not yet reacted in the right way to it. Same summer, this is just an extreme rainfall that was not seen like that in Germany. That's close to where I grew up. And within one night, 200 lives were lost because that river was swelling up to an extent never seen before. At the same time, going a little bit further south in Europe to Greece, Greece was on fire in a way. And just looking at the expression of that woman tells you that these are not abstract features that we are observing. They touch lives and they take lives. So this is something that we often forget when we hear the news. After a few days, the news are gone and we are moving on, often with business as usual. Just a few more examples. Greenland ice melt in 21. In 4 days, 18.4 billion tons of ice lost. That is a tremendous amount. It would cover Florida twice. Texas, we had a cold blast coming from the Arctic down. Infrastructure was not ready. It was a major disaster. The power grid completely collapsed. On the large scale, I was down there in Antarctica, Weddell Sea, as part of my work. We knew that icebergs are breaking off because you are putting precipitation onto Antarctica, on the Antarctic ice shield. It has to go somewhere, and it goes into the ocean and breaks off. But it's breaking off now at a higher rate and at sizes that we are not used to. That's the size of Mallorca. So these are tremendous masses of ice that are breaking off. Close to here, coming closer to today, 2022, we had a drought that was the worst in 12 centuries. If we are looking just a little bit west from Arizona, you probably have heard about the floods that are taking place right now. And keep in mind, we are not in an El Nino year where you would expect that. We are in a La Nina state. So this is really something that is giving us some pause to think. And again, if you look at the pictures, of course, all of that looks terrible in terms of loss of infrastructure, but it also touches humans. Besides climate, and I will finish with that, just giving you a sense of the scale at which we are actually impacting the planet on many fronts. We still have quite a bit of pollution happening. When I grew up, I saw rivers on fire because we had too much pollutants in them, and just a cigarette butt could put them on fire. We still do that. We are soaking our planet in chemicals without really knowing exactly what that means in the long run. Societal stability, I already mentioned. There is quite a bit to think about. If societal stability is not given, and we get quite a bit of chaos on that front, nobody thinks about climate. Everybody thinks about how can I actually survive, how can I move on with my life. And we do see the Greta Thunberg here, you all heard about that the younger generations are increasingly making us aware that we are taking their future away. So that then raises the question, how far can we actually push our boundaries? We have temperature rise, we have a lot of carbon in the atmosphere. This leads to ocean acidification. But at the same time, we have societal pandemics, we have economic disruption, wars, and knowledge access gaps, inequity across the planet. It's almost like we are pushing. So what I often say is we are living in the buffer zone of our planet. We have actually moved beyond what we can extract in equilibrium. And it's almost like driving a car on red, not knowing how big our reserve tank is. That's a very uncomfortable situation to be in. And we have to really take that serious if we are not willing to leave the fate of the future generations to the planet and its capacity to self-regulate, which in essence would lead to the elimination of a significant part of population. So, having looked at the problem, of course, the question comes up, how much time do we have to address that? And that brings me back to climate, because for climate, we have a pretty good timeline laid out with actions to get to that timeline attached to it. So, for example, sea level rise would, if we are not abating it, might force us to, or humankind, to relocate Jakarta, capital of Indonesia, by the middle of the century. We are often talking about the 1.5 degree limit, and I will get to that in a little bit more detail in a moment. We could have a single year of a 1.5 degree warming as early as a few years from now. We are on such a trajectory. So now what is the timeline really? Here you can see on the x-axis time going up to 2100. We are around here. This was done when AR6 was released, the Intergovernmental Panel on Climate Change Assessment Report number 6. And they lay out a scenario to keep us somewhere below 2, ideally at the 1.5 level. And so if we are looking at 1.5, we are looking at that envelope here, that is the blue. There is a pathway that we can think about to get there. And that would mean that by 2030, 7.5 years from now, almost 8 years from now, we have to halve emissions. We have to cut them by half. We also need by 2050, roughly the middle of the century here, we need to take some of the carbon back out to the atmosphere. Even if we cut emissions and we get to emissions close to zero, we have overshot with our concentration of CO2 in the atmosphere. We have to take some of it back. So we have to, how much you might ask, we have to take back roughly 20 gigatons per year, which is about of CO2, which is about half of what we are emitting today. So these are massive amounts of CO2 that we have to take out. Part of that we have to do with nature-based solutions, increasing biomass on the planet to bind carbon. The other half we have to take out with technical means. So that was, at that time, there was hope that we actually have a path forward. What that actually means is that in order to reach one, or to stay at 1.5, by the way, in my opinion, we will not be able to hold at 1.5. I think we actually have crossed that line. We are now focusing more, in my view, we should focus more to stay below 2. I don't think that 1.5 is realistic anymore, because what that would mean is we only would have 300 to 400, let's take a round number, 400 gigatons of CO2 left to be emitted. And that is just about 10 years worth of emissions. At this point, emissions are still rising. So we have not yet turned the curve. If we are looking at 2 degrees Celsius, that would give us about 3 times the amount, about 1,200 gigatons. Even that is not a lot. If we are looking at what we are emitting annually today, it would be 30 years worth of today's emissions. So you can see why I said, you know, that the time scale is really pressing upon us. But if we are then looking what that situation means, if we are decarbonizing the energy industry, if we are looking at different ways to produce energy, there are a lot of opportunities for new economies. There is the transformation of the energy system will create opportunities. For example, electrification of cars, taking CO2 back out of the atmosphere, just to take 3. These are all trillion-dollar industries that can be built. So changing our way moving forward does not mean that we have to sacrifice. It offers quite a few opportunities. We will live differently, but humankind always has evolved. We moved from walking to using horses, to using cars, airplanes. So that there's always change. If we are not making the changes needed to keep the climate at, let's say, 2 degrees or less, then we will see more and more phenomena that will have severe impact on how we can live on the planet. And I just want to come back to this, because we often are saying, you know, 1.5 degrees, 2 degrees. For many people, it's a very abstract number. What it really is the following, or how you can put that into context, the following. Between glacial and interglacial cycles, so here we have the ice volume, here we have temperature. You can actually see that there were about 5 degrees Celsius difference between a full glacial and a warm period. So 2 degrees Celsius, if we just take that as a number, is 40% of a full swing. When you look at how the world was different during the last glacial period, there was about 1 kilometer of ice where now is New York. So 1 degree Celsius, 2 degrees Celsius, although we are going into the warmer direction, is a tremendous amount of warming. We don't feel that because the day-night cycles, which is weather, not climate, are so large. But the planet is very finely tuned and very finely balanced. And we are putting perturbations into it that actually are of a significant amplitude. So I will skip over that. So what does that mean for us in terms of what can be done? The first problem that we see is that we have made decisions that got us onto a track that brings a lot of negative impacts upon us. The question is, are we willing to make different choices? So when we are looking at the climate problem or any environmental problem, it could be water, it could be food security, it could be biodiversity, ecosystem services, we have to deal with a growing population. Pressure on the Earth system is increasing. We are looking for solutions, mitigation, adaptation. We are looking whether or not, if we find these options for solutions, if they are economically feasible, and we are looking at whether or not we have institutions such as the UN who can implement them. All that is necessary, and we spend a lot of time on researching them, but they are not sufficient. If we don't understand how people make decisions, what the so-called societal will is, how we can get to value systems, how can we change value systems, all of that knowledge becomes less useful, you could say almost meaningless. So that's, as we are looking at solutions to the climate problem, we need the technical solutions, we need the nature-based solutions, but more important than all of that is we need a change in the mindset. We seem to see that in the younger generations. The question is, what is their staying power and what are we doing to support them rather than fight them? I talked about that. I just will bring a few examples to highlight what we actually are seeing in the climate system that is a hotspot of climate change. And I already showed you that temperature map of the Earth that has much higher warming in the Arctic, in high northern latitudes, by a factor of 2.5 more. So if the global, if we have global warming of 2 degrees Celsius, the Arctic warms by 5 degrees Celsius. That's a full swing of the glacial interglacial cycle. So, and this was recognized a long time ago in 2001, that there are certain feedback mechanisms in the Arctic system that will lead to a more rapid and more severe change of climate than the rest of the Earth. So the question is, are we seeing that and how are we doing that? This is just to give you a sense of how we are exploring the Arctic. These are all expeditions that I was either on myself or members of my group, where we visited all of these stations here and probed the ice, the atmosphere, and the water underneath the ice to see what kind of changes are actually going on. And one of the most iconic pictures that you can see in satellites is the decrease of the sea ice extent in the Arctic. So if you're looking from 79, which is actually the beginning of satellite observations, to that's 22, you can see that decrease. Again, it's a complex system, it's a natural system, it has variability, but a clear trend of about -13% per decade of the decrease of the ice cover. So what that means is that if we are looking at our models that simulate that by 2100, depending on which scenario we are using, we have about less than half of the sea ice cover left. Maybe we are opening up the Arctic Ocean altogether. That has tremendous impact locally, how people can live off the ocean from the ice, and how we are globally, how are we navigating, because the shipping routes through the Arctic are starting to open and are being explored. We're looking at Greenland. You can see that there is more melting on Greenland happening from the fringes towards the interior. Here is 2020 melt percentage. Here is an average. So we are pushing that up too. And this was something that really was amazing to me, that in 2020, there was, sorry, no, that was not 2020, 2012, there was, within a few days, the melting went from where we usually find it around the edges to cover the entire Arctic, the entire Greenland ice sheet surface. The runoff from that, the water that was melted, washed bridges, structures away in the cities and towns around the fringe. So the other thing that we have to keep in mind is Greenland holds about 2.8 million cubic kilometers of ice. If we would melt Greenland, that would be 7 meters, 20 feet in sea level rise globally. So there is something that we have to watch, because what we are seeing is this is not just following simple thermodynamic laws. The way ice is shed off Greenland into the ocean is by increased heat. We have more melt ponds. They find their way into crevices, cracks in the ice, and some of them are now so mighty that they actually go all the way through. We know that because people like my dear colleague and friend, Conny Steffen, who actually died while doing that research, went down these so-called moulins and found that they reach the bottom of the ice sheet. So that gets the water from the top to the bottom. It's almost like making it more slippery. It moves faster towards the ocean, then it breaks off. So these are the things that we are seeing. There are also glaciers that are, if you look here, 8050, that's Jakobshavn Glacier in Greenland, and 2016, it's completely gone. That was like a resistance to keep the ice on Greenland rather than letting it slide in the ocean. So we see more and more scientifically, but also in the way we live, what we experience in terms of the severity of this issue. I will skip over that. So if we are looking then at people who are living in the Arctic, for them, this is not abstract. It's warming, the permafrost is thawing, the coastline falls into the ocean, and with it, their structures. So they have to actually be relocated, or they give up and migrate away from that. That is something, that's Shishmarev, it's also new talk. This is something that is happening more frequently now. So the question then, the next question, so we have seen the underlying reasons, we have seen the impacts, we have seen the timeline. The question is, what can we do? And there is quite a bit that can be done. We do in principle know how to transition in an orderly fashion from mostly fossils to renewables, wind, solar, some geothermal. This has to be done really carefully. We cannot do that too fast, otherwise we will have energy gaps. We still have a very low percentage of renewables in the total energy mix globally and in any region that you look at on the planet. But that trajectory has to build up exponentially for the renewables, and we have to phase out the fossils in the next, let's say, 3 decades in an exponential fashion. We also know in principle that we can remove carbon from the atmosphere. That's an artistic depiction of a device that was developed out of ASU with a company called Carbon Collect, and we have the prototype sitting actually outside the building from which I'm talking here. We also have to optimize material cycles. We are taking way too much out of the planet, including fossils, and are not using it frequently enough. So we have to reduce the extraction, increase the reuse cycle, increase the recycling cycle, and minimize what we put back into the planet as waste. So we have a good feeling for how to do that. This is material about the Global Futures App. I will skip over that in view of the time. Just show some of the things. So this is one of these Tiburios that take CO2 back out of the atmosphere. So that's one thing that we are driving from here. Another thing that has to be done in getting out of the climate crisis, but also the other crisis that we are in, is we have to integrate knowledge systems. We cannot say that science is the one and all. Science itself actually has to figure out how to gain the trust back within society. In the US, which is probably a bit an extreme case, the trust in science is at an all-time low, I would say. In Europe, in Asia, we have more willingness to listen to what science says as a guiding principle for how we might move forward. But in general, academia has lost the trust of people we are often seen as an elite that does not understand what the problems of people on the ground are, and we have to really start to engage. And now I'm actually going back to one of the figures. If you look at academia, and I'm using here the Global Futures Lab, but it could be any other academic enterprise, we are typically good at discovering new insights, new knowledge. One of our mandate is to teach learners from pre-K to seniors. We are increasingly trying to put that to work for solutions to the problems that we have created, and we are starting to network because the problems are too big. All of that still could be done without a real impact on the world. So we added in our, what I call spaces of engagement, the engagement space, which means we have to listen to the outside. We have to have conversations that allow us to gauge where are the biggest problems, where are people feeling the biggest pressure, what does that mean for our research, what does that mean for the time scale at which we have to deliver, what does it mean for delivering incomplete knowledge, what kind of profiles do we have to train to address their problem, and how to really become much more a part of society than we are right now. So back to this, there are indicators of planetary health, such as corals. So we are monitoring the global, the corals, the coral reefs globally, to see what are they doing under the pressure of heat, acidity from having CO2 in the ocean, pollution, different use of the fisheries, different use of the areas in which they are, to make sure that they are not eroding completely, because they have a lot of functions that help the climate system and they help the ecosystems, biodiversity, etc. There is a lot we know about energy, about how to create alternative energy, how to do it on very small microgrid levels, how to do it on a more global scale, regional scales. We have to make sure that we are actually doing that in an ethical fashion, a much more equitable fashion than in the past. So these are things that in principle are known, but our action on it is not fast enough. This is one of the final figures here. In a lot of the decisions we have to make about how to move into the future, science has to provide support for those who have to make the tough decisions. So that's what we call decision support. Increasingly, academia has to engage in informing those who are sitting at the levers, who are making the decisions that shape the planet in the future, and give them the knowledge that we have to offer, even if it's not complete, if we tell them in which way it's not complete. So that is something that is increasingly important, that we engage and become, decision support. That's my last figure. So you all know that Phoenix is hot. Phoenix is the hottest, and Tempe is next to Phoenix. So that's from where I'm talking. The hottest city in the US, has the highest number of heat-related deaths in summer in the US. Between 300 and 500 people lose their life because of heat. And it's, if you are looking here at 1900 to present, you can see that these are the blue colors are cooler temperatures, the warm colors are warmer temperatures. If you eyeball that, it's about 5 Fahrenheit, about 2.5 Celsius. 1 to 1.2 is coming from global warming. The other half is actually from local impact. If you look at all these concrete structures, they take in solar radiation during the day and radiate it off at night. And you can actually feel it. Much warmer if you walk within that structure or if you go out into the desert. So here again, we have to figure out, how are we building in the future? How densely, what materials, what colors, what can we do actually to take some of the pressure off that we are inducing upon our environment and thereby ourselves? So to conclude, global change is progressing. We are feeling it more and more. the impacts of climate change are more visible, more extreme. We have pushed our planet to its limits. The planet is telling us through these extreme events that it is at its limits. Crises are coming more frequently and at a greater cost. And at the same time, we have an opportunity using our knowledge to change the way we behave. But we have to do it now. And now does not mean we are starting to think about it for 10 years and do something now. We are actually behind the timeline, so we have to do it now. But in a way, it is truly up to society to make the right choices to get us back on track. If we are not making these choices now, then what I mentioned before, I see that the planet self-regulates. The planet itself, if you look Earth as a planet in its entirety, can perfectly live without people. People cannot live without the life-supporting systems that our planet provides. So we have to understand that we are part of a complex system, that we have perturbed, we have overused part of it. We have to get back into balance with what some people call nature, what I call the life-supporting systems of us. So with that, I would like to conclude my remarks. I thank you for your attention.
Thank you so much, Peter, for an absolutely wonderful presentation. What struck me as you were talking about the science and the role of science in society was how far we've come since a few decades ago, when a few scientists in a few companies in the world knew what was happening as we burnt fossil fuels. And that was held in secret. To these days, when more of the world and more average citizens are now aware of the incredible damage we are doing to our home. So we are at a stage where knowledge is no longer in the hands of a few, but in a larger range of people. Needless to say, the extent to which that knowledge is causing the kind of change in mindset, we have to pay attention to that. And your point that you made about the importance of young people participating and giving young people that space to actually participate in this dialogue and actually to influence and shape the future that is theirs is so very important. A couple of questions are coming in, but I want to ask if you can give a little bit of context to nature-based solutions. So you mentioned the kinds of work that ASU is doing in relation to understanding the impacts of climate. And then you also spoke of the technological solutions. But as you also pointed out, it's a combination of nature-based solutions alongside the technologies that will actually make a difference. So I wonder if you could just spend a couple of minutes talking about what ASU is doing in relation to nature-based solutions.
So on the nature-based solution side, we are working closely with Conservation International to understand how much biomass can you build up. Because if you look at it in a fairly simplistic way, we can, of course, grow trees. You all heard about the Trillion Tree Initiative and afforestation, things like that, reforestation. Also increasing the organic material of soils, which also could help with the production with the food production. So there is capacity, but it's also true that this capacity has a limit. And we are working on figuring out exactly how much that is, because once you reach a certain level, you just saturated the ecosphere and you cannot put more CO2 in it. In terms of the pace, we probably can make faster progress with nature-based solutions than with the scaling up of the technical solution. But at some point they will cross, and the nature-based and the technical solution has caught up. the technical solutions to take CO2 back out of the atmosphere, in principle, don't have a limit. In principle, we know how to do it. There are several companies now that have produced pure CO2. We also, in principle, know where to put it, and it has demonstrated that it works to put it underground. So, but these two things have to be in balance. We have to get out of nature what we can without damaging it in another way, and the rest has to be done with technology. So I'm not somebody, although we developed the technology for taking CO2 out of the atmosphere, I would not say this should be our primary goal, but we have to be ready to apply it, because we do know at this point that nature alone cannot do it.